Hello, my name's Dan Larremore. I'm a professor at the University of Colorado Boulder's Computer Science Department and in CU Boulder's BioFrontiers Institute, where I study questions of where data science comes into contact with infectious disease epidemiology. And really, I'm a mathematical modeler, and some of the questions that we've been asking these days really show how, when it comes to the COVID-19 pandemic, data scientists and mathematical modelers are really there at the forefront. So I want to tell you about two questions that we've been addressing quite recently in our research. The first one is on prioritizing vaccines. The big question with prioritizing vaccines is who should get them first and why. And there are two general theories that I think make a lot of sense that really appeal to our common sense notion of how we might think about a vaccine. The first one we can think of as direct protection. So in this case, direct protection means that we should give those early vaccines to older adults. The logic here is that we should protect the vulnerable. On the other hand, it also makes a lot of sense to use a strategy called indirect protection. With indirect protection, we're going to give the vaccines to working age adults and young adults, and those folks who are most responsible for transmitting the virus. And in this way, we protect everybody, not just those older adults, but everybody else in the population as well. And the logic here is to break the backbone of transmission. So this is a situation where common sense actually points us in two opposite directions. One, direct protection, that makes a lot of sense. The second one, indirect protection, that also makes a lot of sense. And anytime your common sense actually points you in two opposite directions, that's a great example of a time when you should really not be making decisions based on common sense, but instead you should be using data in a mathematical model. So our big question in this first research project was, what's the right path for COVID-19 vaccines? There are a few data sources that we really need to grab hold of in order to make this decision. The first one is that we need to understand data on population mixing. So on the left and right here, I'm showing you what we call age stratified contact matrices from two countries, Germany on the left, South Africa on the right. And in these heat maps, what you can see are contact patterns between people of one age versus another age. So you'll notice a few things. Let's go through some of those. First of all, across the diagonal, you'll notice that there's a lot more density here. And that's just because people tend to spend time with others who are of a similar age. In Germany, plus or minus 5 years along this diagonal. But you'll also notice these nice off-diagonal patterns. Do you know what those are? These are the contact patterns between adults and their children. Notice that it's really these 20 to 35-year-olds who are spending time around 0 to 5-year-olds, and so on. And as the kids get older, the adults get older as well. If you contrast the situation in Germany to the contact patterns in South Africa, you can see that the age-based population structure is just very, very different. For instance, in South Africa, you can see the connections between kids and their grandparents, suggesting that kids and grandparents come into contact a lot more often in South Africa than they do in a place like Germany. And so what you might imagine is that if we're thinking about prioritizing the vaccine, it's going to be really important to have this data in hand so that we know whether or not we're vaccinating for Germany or South Africa. The contact patterns are going to make a difference because we know this is a disease that spreads through contact patterns. Now, these data were originally collected for influenza, but have been since very useful in understanding how we should prioritize vaccines for COVID. Another important data point that we need is really a curve, which is the deadliness of the virus by age. So on the horizontal axis here, this is the median age of people in a number of different studies. And on the vertical axis, this is a log scale of what we call IFR, or the infection fatality rate. This is the probability that somebody dies given that they were infected with the SARS-CoV-2 virus, given that they had COVID-19. And one thing that you can see is that we get, over all of these different studies that are being plotted here, in the meta-regression, something that looks basically like a straight line. And if we have a straight line on a plot with a log axis, that of course means that we have exponential growth in the probability that you die because of COVID as you get older. Or if you think of it the other way, exponential decay in that probability as you get younger and younger. So if we have those contact patterns, and we know that COVID-19 really affects older adults far more severely than it does younger adults based on this plot, now we can start to put these together into a modeling framework. So these interact with strategy in the way that we can specify some strategies like, what if we give the vaccine just to those under 20? Or what if we give the vaccine to those working age adults, call them 20 to 49? Or all adults, 20 plus? This green panel in the middle here is what the vaccine has been approved for currently in the US. What about older adults first? Or maybe we just give out the vaccine to anybody who wants it, all ages. Depending on these different strategies and how they interact with the contact matrices and the infection fatality rates, we may get different outcomes. And so that's what this first study was all about. It involved modeling, it involved wrangling data from many sources at once. We also had to quantify uncertainty and do a lot of sensitivity analyses to understand whether or not our findings were really robust to slight changes in the assumptions in our models. Then, of course, the final pieces that were critical, science communication, including communication of that uncertainty to the news media and policymakers. We really had to be thinking about policy and policymakers up front. So if you want to learn the conclusions of our study, you can check it out in Science magazine. The title of the paper was Model-Informed COVID-19 Vaccine Prioritization Strategies by Age and Serostatus. And that includes all of the information that we've talked about here today. The punchline, of course, is that who you should prioritize with the vaccine depends on what are the transmission patterns. What is the age demographic composition of your population? What are the contact patterns in that population? And of course, how much vaccine do you have and how quickly can you roll it out? So for the second topic here, I want to touch on one complication that we know about with this pandemic, which is human mobility. Like, where do we carry our viruses? The viruses can't hop on a plane without us taking them with us. So we have to realize that transmission is also spatial, right? We carry the viruses or the bacteria or anything that we have with us wherever we go. So for example, in the beginning parts of the pandemic here in Colorado, there was this question of ski tourists who were bringing in a lot more virus into those high altitude mountain towns where people were going to ski. And that was because there was a lot more spatial mixing of people who were flying in for vacation and for spring break. So in this study, we were asking, how has COVID changed our behavior? So we teamed up with Facebook's Data for Good to study human mobility and population density. We collaborated with local departments of public health to help them quantify risk and learn the impacts of their policies. So especially in March 2020, April 2020, and May 2020, when there were a lot more movement restrictions, it was really important for policymakers to understand, are people actually following the rules that we put out there, or are they still going about their business? So what we did was created a lot of these population density maps based on logins to Facebook. And so in this heat map, you can see red areas where there are far more people than in a typical March, and in blue, areas where there are far fewer people. So you can see really the downtown Denver area had completely emptied out, as had downtown Boulder. But some of these suburbs and bedroom communities were far more populated, suggesting that people were in fact staying home and spending some of their time on Facebook, which Facebook's Data for Good picked up. I want to point out here, though, something critical in data science, which is that we need to respect privacy. And so I'll just point out that all the data here were aggregated and anonymized. So you'll notice there are a lot of gray areas on the map. In those gray areas, there were so few people that to provide us with any data at all, Facebook would have violated the privacy of the individuals who were there. And as a researcher, I have no interest in that. And so, of course, this is a project that brings together these ideas of differential privacy, where by adding a little bit of noise and by aggregating individuals across tiles, we make sure that we can never actually see any individual person and track them through. And this is another example of just an enormous data set and a partnership with industry, and the importance of creating easy to understand visualizations and clear dashboards for departments of public health and policymakers. So if you're interested in learning more about this study, this was published as a workshop paper, and it's called Case Study, Using Facebook Data to Monitor Adherence to Stay-at-Home Orders in Colorado and Utah. So in sum, this is really all about data science for policy impact. There are two studies here, one about vaccine prioritization and the other about using some spatial modeling to understand the impact of those stay-at-home orders in 2020. But it brings up all these key points from data science, modeling data, wrangling data, uncertainty quantification, communication policy, privacy, industry, and visualizations and dashboards. So of course, if you have any questions about this work, you can get in touch with me. My email address is down at the bottom of the screen, daniel.larremore@colorado.edu. And thanks for the attention.